Hey everyone! In today's video, we're diving into how to create your first custom block in GNU Radio. Let's jump right in and get started. Contents: Introduction, Opening Code Editor, Components of a Python block, Changing parameter name, Editing block inputs, Editing work function, Connecting the flow graph, Running the flow graph. Conclusion. Introduction. This presentation shows how to create a signal processing block with the embedded Python block. The example block either adds or multiplies the two inputs based on a parameter. This presentation uses the embedded Python block, which can only be used in the flow graph it was created in. The tutorial Creating Python OOT with grmodtool demonstrates how to create a custom Python block as an out-of-tree OT module which can be installed and used in any flow graph. Opening Code Editor. The embedded Python block is a tool to quickly prototype a block within a flow graph. Search for the Python block and add it to the workspace as shown in Figure 1. Double-click the block to edit the properties. The embedded Python block has two properties: code, a click box which contains a link to the Python code for the block, and example parameter, an input parameter to the block. Click on Open in Editor to edit the Python code as shown in Figure 2. An editor window displays the Python code for the embedded Python block as shown in Figure 3. Components of a Python block. There are three important sections in the Python block code. 1. Import statements in a green box. 2. __init__ method in a blue box. 3. Work method in a red box, as shown in the Figure 4. Components of a Python block continued. The import statement includes the number py and GNU Radio libraries. The _init_ method. 1. Accepts the example _perm parameter with a default argument of 1.0. 2. Declares the block to have a np.complex64 input and output, which is the GNU Radio complex float 32 data type. 3. Stores the self.example_perm variable from the input parameter. The work method. 1. Has the input_items and output_items parameters. 2. Applies a mathematical operation to input_items and stores the result in output_items. 3. Returns the number of samples produced. Components of a Python block continued. The remainder of this presentation will describe modifications to both the init and work functions to demonstrate how to provide custom functionality. The init and work functions cannot be changed arbitrarily as they must conform to the rules and expectations of the broader GNU Radio software framework, which controls transferring data between block inputs and outputs. For example, the number of input parameters to the init function can be changed to include the different number of variables being passed into the block. However, the work function must use the pre-existing function definition, which includes input_items and output_items, and in the correct order. Additionally, the embedded Python block must return the number of output samples produced, which must be equivalent to the number of input samples produced. Changing parameter name. The code is modified to add the custom behavior. The first step is to rename example_perm to addition flag as shown in Figure 5. The parameter is changed. The Python code is updated as shown in Figure 6. Changing parameter name continued. Change the default value to be true, so a truth value instead of the floating point number 1.0, as shown in Figure 7. Return back to the GRC window. The embedded Python block displays the addition flag parameter instead of example_perm as shown in the Figure 8. Editing block inputs. The default block has a single input and a single output. However, we need two inputs for the block. To add an input, add a second np.complex64 np.complex64 to the in_sig list as shown in Figure 8. Change the block name to add or multiply block as shown in the Figure 9. Save the file. GRC displays the block with a second input, and the block name is updated as shown in the Figure 10. Editing work function. The work function needs to be modified. The pseudocode for the Python block is as shown in Figure 11. Modify the work function so it has the following code as shown in the Figure 12. Then connecting the flow graph. Return to GRC. Double-click the add or multiply block. Enter true for the addition flag property as shown in the Figure 13. Connecting the flow graph. Continue drag and drop two signal source blocks, a throttle block, a Qt GUI time sync and a Qt GUI frequency sync block into the GRC workspace and connect them according to the following flow graph. Set the frequency of the second signal source to 3000 as shown in Figure 14. Running the flow graph. Selecting True in the Add or Multiply block performs the addition of the two signal sources. The plots show the summation of the two sinusoids, one at a frequency of 1000 and another at 3000. The y-axis in the Qt GUI time sync plot is shown in the Figure 15. Running the flow graph continued. Enter false for the addition flag property as shown in Figure 16. By definition, the multiplication of two complex sinusoids produces a sinusoid at the summation of the two frequencies. Therefore, the multiplication of the signal source of frequency 1000 and frequency 3000 is a complex sinusoid of frequency 4000. This complex sinusoid is seen when running the flow graph as shown in Figure 17. Conclusion. This presentation covered the basics of working with Python blocks in GNU Radio. You learned how to open the code editor, understand the components of a Python block, and make simple edits to parameters, inputs, and the work function. Finally, you saw how to connect and run the flow graph. With these basic skills, you can start customizing Python blocks to fit your needs in GNU Radio. Thanks for watching. If you found this helpful, don't forget to like, share, and subscribe for more GNU Radio tutorials. See you in the next video.